Okay, so today's video is to take a look at basic properties of acids and bases, how we recognize acids and bases, and then a couple of different systems used to identify what acids and bases are, to define kind of what's an acid or a base. So in terms of what they are, a bit of review first. I wanted to remind you about how to name these guys. I know it's something that we learned a long time ago, but I figured it was probably a good chance to go back and check them out. When you're talking about bases, don't forget, most bases are pretty straightforward. They contain the OH ion, hydroxide, and so their names are really pretty straightforward. The other one that I need you to know, however, is a base, is the one known as ammonia, which is NH3. Not ammonium, which is NH4 plus, it's an ion. Ammonia is a molecule, so keep that in mind. Those are your common bases. In terms of acid names, just a quick review. If you get a binary acid, it's hydrogen and a nonmetal all by themselves. Those have the name of oic acid, so hydrochloric acid, hydrofluoric acid, hydroiodic acid, hydrobromic acid, those kind of ones. Oxyacids are the kinds that have some sort of a polyatomic ion, like hydrogen and sulfate, hydrogen and nitrate, hydrogen and phosphate, etc. If they're the 8 forms, remember that the ending is changed to ic acid. So if it was hydrogen sulfate, it would be called sulfuric acid. Hydrogen carbonate would be called carbonic acid. If it's the ite form, which we're really not going to deal with in this chapter, so don't stress about it, but if it's that ite form, the slightly lower number of oxygens to it, it becomes OUS acid. So if it's hydrogen sulfite, it would be sulfurous acid, or nitrous acid, or chlorous acid, kind of weird ones. We don't see those very often. The only organic acid you have to worry about is acetic acid. Acetic acid and all the organic acids have this thing called a carboxyl group. That's the Cu group, C double bonded O with an OH on it. And acetic acid is the one that you know that falls into that group. So down at the bottom here, there's your list of stuff that you really do need to know, those names and formulas, so make sure you check those out. And then the last thing up here is some differences between acids and bases. You know, how do you know if you've got an acid if it's chewing on your ankle, or not? So if you're talking about acids when they're in solution, not when they're dry salts, but when they're dissolved in water, they conduct electricity, so do bases. They have particular ranges of pH. Typically with our universal indicators, they're on that red range of pH. Bases tend to be on the blue range of pH. Acids tend to be sour, so think about lemon juice, citric acid, or if you've ever tasted aspirin before, aspartic acid. Nasty stuff, really, really sour. Bases tend to be really bitter if you taste them. So coffee is actually a base, is a good example of one. Soap is a bitter base as well. Usually both of them, they will react with one another to neutralize. So if you have an equal amount of acid and base, they add up to 0. One of the weird things that is about acids is that acids will react with active metals and fizz. They create a lot of hydrogen when they do that. So if you can remember that acids are typically sour, bases are typically bitter. Bases also tend to be slippery when you touch them, so think about soaps. And those kind of overall sort of pH colors that you've got, you're in pretty good shape. Okay, there's 2 major models for defining what an acid and a base is. Arrhenius Model, that's how you say that guy's name, was kind of the original. He was working with a variety of things called electrolytes, solutions that conduct electricity, and he was trying to come up with kind of an idea for what an acid or a base was. He actually won the Nobel Prize in Chemistry around the turn of the century for this, and his idea was that an acid, kind of like what we've already talked about, acids produce hydrogen ions when they're in solution, and bases produce hydroxide ions in solution. Pretty straightforward. I mean, this is, like I said, they work for about 90% of the acids and bases that we deal with. But this is Arrhenius' model. Both of these tend to be strong electrolytes because they're producing those ions in solution, so lots of electricity can travel through those solutions. However, there's some cases where this doesn't work. And this is where these next 2 guys came along. Bronsted and Lowry came up with a slightly wider definition of what an acid and a base are. So they defined acids in terms of protons. So an acid's a proton donor and a base is a proton acceptor. So this works in cases where there isn't just hydroxides present. Remember, a proton and a hydrogen ion are the same thing. So to say something's a proton donor or to say that it has a hydrogen ion to it, it's basically synonymous. The base's definition is actually what's more different. So things like NH3, which is ammonia, the reason why it acts like a base is due to its Bronsted-Lowry model, that it accepts protons. It does not have a hydroxide, so it doesn't really work that way. But anyway, keep in mind, there's one other thing that we need to understand here, a little addition that Bronsted-Lowry had, is that they said that when you have acids and bases in solution, that hydrogen ion didn't kind of wander around freely. It actually bonds with water molecules that are present to form this really bizarre creature called a hydronium ion. Hydronium ions is formula-wise is written like this. It's H3O+. So those hydrogens don't stay by themselves. They actually form hydronium. Kind of a crazy word. But that's a Bronsted-Lowry definition of what an acid is. going along with this, they said that you could kind of analyze the before and after parts of an acid and base in a reaction. That an acid, which is a proton donor, will have something left over at the other end of that reaction. So if you take a look at this equation that I've got here between HCl and water, that if I take a really strong acid like hydrochloric acid and dissolve it in water, which it typically is, that hydrochloric acid is going to donate a proton. It's going to donate it to water. But once it's donated that proton, what's left? Well, this chloride ion is what's left after it's donated. Same thing, that hydrogen, the water here, is going to receive that proton. It's going to accept it. So the water actually acts like a base in this case, which is kind of an odd thing. But it's going to accept that proton, and after it's accepted it, it's going to become this weird thing called hydronium. So we can kind of talk about the before and after. Hydrochloric acid in the beginning as a reactant is an acid, and water at the beginning as a reactant is a base. However, what's left when we're done, we put some different names to these things to kind of give them their special idea. We would call these things conjugate acids and conjugate bases. A conjugate acid is what's left over after a base receives a proton. A conjugate base is what's left over after an acid gets rid of it. So an acid becomes a conjugate base, and a base becomes a conjugate acid. Why are they called that? Why isn't it just called a base becomes a conjugate base? Well, if you take a look at the reverse reaction, so consider this reaction going the other direction, you can see that this H3O is going to act like a proton donor to become H2O. So if we talk about it in the reverse reaction, that H3O acts like an acid. So that's why it's a conjugate acid if we talk about the typical forward reaction. So it's a little bit weird. But you'll be asked on the test to be able to identify or name, label conjugate acid, conjugate base pairs. Keep in mind the only difference between a conjugate acid base pair is one hydrogen. That's the only difference. Nothing else can change. It cannot be more than one hydrogen, can't be oxygen, can't be nitrogen, can't be anything else. Simply one hydrogen is going from one thing to another. And there's a kind of a group of little examples over here, so you should probably hit pause, take a look at that, and see if you can understand why those things are called conjugate acids and conjugate bases, because on the next page I think I have some practice problems for you. All right, so here you go. Take a look at these problems. I probably should hit pause. You might want a piece of scratch paper to figure this out. But your job is to take a look at each of these reactions here and see if you can answer these questions about conjugate acids, conjugate bases, acid-base pairs, that kind of stuff. So your job would be, and I'll show you the first one as an example, to analyze one of these equations, like this is the equation of carbonic acid dissolving in water to produce this bicarbonate ion, HCO3-, and a hydronium ion. So the question becomes, what's the acid, base, conjugate acid, and conjugate base? So here's my answers on here, so you can kind of take a look at it. This one's the acid, because here it's proton donor, and there's the conjugate base that's left over. Here's the base, because it's a proton receiver, and so there's the conjugate acid that's left over. So hit pause, see if you can work out the rest of these problems, and I'll come through and go through the answers here with you in just a second. I hope you hit pause. I hope you didn't just wait for me to sit there. So here we go. In terms of this one, this is ammonia plus water yields the ammonium ion and the hydroxide ion. So here's our responses here. Ammonia acts like a base because it is a proton receiver, and here's the before and after. That we've got ammonia here. Sorry, there it is. And then ammonium there. So this is a conjugate acid because it's got that extra hydrogen that's attached to it. In this case, water acts like a base because here it is here, and then there it is afterwards. It's donating its proton, and what's left over after it gets rid of that proton is a hydroxide ion. All right, this thing. The sulfur ion plus bicarbonate ion yields hydrogen sulfide ion and carbonate ion. So what's that? These look really strange when you do this. Again, look for where the hydrogens are changing. This S, the sulfur ion here, is a base. It's a proton acceptor, and here it is. It's now accepted that proton, so now it's a conjugate acid. This HCO3 is what's giving away, so it's the acid, and here's what's left over, so there's its conjugate base. And then the last one, this is ammonia plus acetic acid, gives us acetate and ammonium ions. And again, hopefully you got this one right. This is the proton receiver, so it is NH3 to NH4. This is the proton donor. Acetic acid is the proton donor, so it's CH3COOH, and then just CH3COO. So there's your before and after. What's your conjugate base of H2SO4? Okay, in order for it to be an acid, it's going to be giving something away, so it should be HSO4-. It's not an ion I know you're super familiar with, but remember, only one ion can change, one hydrogen only. How about the conjugate acid of OH? Well, that'll be after it's received, so that's going to be simply Water. Hydroxide, once it's gained one, is a hydroxide bit. And then are these two a conjugate acid-base pair? The correct answer is no. They're close, but not quite. They're not actually a conjugate acid-base pair because two hydrogens would be moving back and forth, and a conjugate acid-base pair only has a single proton or a single hydrogen that's taking place. All right, moving on. So let's take a look. Different topic here. It's this idea of strong and weak acids. Strong and weak acids is a little bit of a confusing topic because strong and concentrated don't mean the same thing here. A strong acid is something that ionizes completely. It releases all of its hydrogen ions. All of those hydrogen ions are available in solution to go and react with things. Weak acids, on the other hand, tend to hold on to their hydrogens pretty tightly. They only let a few of those hydrogens out into reaction. They kind of hold on to them pretty well. They don't want to let them go. So over here on the right, we have a reaction of a little piece of magnesium metal and two different acids. So which one do you think is going to be the strong acid and which one's the weak acid? Well, this one on the right here that's got all this reaction going on, this must be the strong one. It's got more hydrogens available to react with that magnesium metal that's in there. This one's a weak one, much slower reaction to it. There can't be as much hydrogen that's present. So here you go. We've got sulfuric, hydrochloric. Sorry, I should cover that back up. Our strong acids, there's only 4. Sulfuric, hydrochloric, nitric, and perchloric. Those are the ones that you're going to have to deal with as far as your book is concerned. You should test yourself. Do you know what the formulas are? There they are. There's your formulas. And all the other acids are classified as weak. So carbonic acid, nitric acid, phosphoric acid, those are considered to be weak acids. They hold on to their hydrogens. Sulfuric acid, hydrochloric acid, nitric acid, those are your strong acids. All right, strong and concentrated, two different ideas. Remember that strong refers to how much they hold on to their hydrogens or let them go. Concentrated refers to how much water are they mixed with. Are they diluted or concentrated? You can have a dilute strong acid, you can have a concentrated weak acid, etc. For example, vinegar is classified as a weak acid because it holds on to its hydrogen, but 27% as a concentration of acetic acid, strong enough to make your eyes water. It's incredibly concentrated, but it's still a weak acid. So again, I know that's kind of a weird thing to think about what that is. Furthermore, we can talk about the differences between strong and weak in terms of their conjugate bases. Strong acids have weak conjugate bases. In other words, strong acids really want to give up their hydrogens. Those weak bases really don't. They want to kind of hang on to those. If you're talking about weak acids, they have the opposite. Weak acid has a strong conjugate base. It really wants to donate that proton. The weak acid really doesn't want to give it up. So it's a little bit different. I'm not going to really ask you in terms of the weak conjugates, strong conjugates, that kind of stuff, but you do need to know the difference between strong and concentrated or weak and dilute, and that's a pretty important topic there. So there you go. There's your main ideas for this particular session on acids and bases. We have two different models of identifying or classifying what acids are. Arrhenius' model works most of the time, and that's acids are hydrogen and bases are hydroxide. But the Bronsted-Lowry model, having to do with proton donors, proton receivers, works in pretty much every single case. You need to be able to identify and see what a conjugate acid, conjugate base would be in a particular reaction. So you will need to label reactions, kind of like the practice problems that were in here. Remember, one and only one hydrogen is going to be moving for a conjugate acid base pair. Strong acids versus weak acids. You need to know that a strong acid releases all of its hydrogen ions. Weak acids do not, and that's what you've got going on between these two. Strong acid goes all the way to ions. Weak acids really don't. When you have a weak acid in water, it's still mostly weak acid, just a little bit of ions are left over there. You need to be able to name all 4 of the strong acids. You need to be able to differentiate between the concepts of strong and concentrated, or weak and dilute. And then if you want a 4, you should probably take a look at another model. It's a little bit more modern, having to do with Lewis's model of acids and bases. And again, a little bit of a different distinction in terms of what they are. Or you could look at why are some acids classified as strong, but other acids are classified as weak. What is the kind of chemistry behind that strength and weakness of different acids? So there you go. I hope you enjoyed today's little lesson about acids and bases, and have a good day. See you in class tomorrow.